We're going to get started. So hopefully the last few people get here shortly. So today we're going to finish up section 3.2. Then we'll look at a couple of examples from previous AP exams for these scatter plots and correlation and regression lines and things that we're seeing in this chapter and seeing how they come up on past AP exams so we can see kind of what that is. All right. And that's kind of the basic idea for today. So we'll start with, where'd my mouse go? There it is. That one. And share my screen. There we go. Go that way. Oh, that's what I wanted. Perfect. All right. So here's where we left off yesterday. We didn't actually show you this screen, but this was the next one. All right, so we're going to be looking at first interpreting computer regression outputs. We're going to see two different computer outputs using two different programs. You're not going to be expected to run or know how to use these two programs, but their outputs might be provided. So you need to know how to read them and which values we're going to use from them. All right, so there are a number of statistical software packages that produce similar regression output. Be sure we can locate the slope, or B, from our y hat equals a plus bx, the y-intercept, or A, and the values of S, the standard deviation of the residuals, and R squared. We need to be able to find these values. So we have in this printout a couple of different categories. We have the predictor coefficient. I believe that's going to be standard error coefficient, T and P. Obviously, right now, based on just what's circled on the screen, we're not using any of these or this. It's not what we're covering right now. Right, the predictor, we can have a constant, which goes along with the coefficient, which is the y-intercept. Right, just like in any linear equation, the y-intercept is represented by the constant term. Right, and y equals mx plus b. B is our constant term. It doesn't have a variable with it, so it's a constant. Right, so our constant, and in this regression equation, is A, and it's 38,257. Miles driven, right, is essentially the variable, or X, and it has a coefficient that's represented as the slope, and this should be negative. I'm not sure how that got left out on this printout, but it's 0.16292. Right, so we have the slope and y-intercept. So just between those two, we have enough to write the regression equation if requested. We also have S, the standard deviation of the residuals. Right, it's the typical distance from the regression line of the points. And our R squared. Right, the R squared is essentially a percentage, a proportion of, kind of represents how well the regression line will take into account the variances of our points. All things considered, how well does it relate my two variables and take everything into account? In this example, it's fairly good. 66.4% of the variances are taken into account in our line. Right? The more spread out your data points are, like the less close they are to the regression line, the smaller that percentage gets. The more concentrated they are, the bigger that percentage gets. Obviously, it has to be a value between 0 and 1, or 0% and 100%, as proportions are. Right? And R squared is literally correlation R squared. Remember, R is always a value between -1 and +1. That helps make sure that this value is always between 0 and 1 as a decimal. All right. So that's this representation. We also have this printout. We can find the same 4 values on this one. And it's from a different program. And here we have our category of like summary of fit. We have R square, which is R squared. They're not pretending on that one. We don't need to worry about this adjusted one. We have the root mean square error, which is the standard deviation of the residuals. All right. And that one, if you're trying to figure out what it is based on how they're wording it, it is the square root of the basically like variance, the square error. Right. We have the mean of the response. We're not using that. Observations. Right. We're not using that one right now. Parameter estimates. We have term, estimate, standard error, t-ratio, probability. We're not using these ones over here. But again, the intercept is the intercept. That's kind of nice. And our miles driven, again, is representing our variable, which has the coefficient with the slope, right? The estimate of the slope. This one turned out correctly. It is supposed to be a negative slope. Again, I'm not sure why it got left off on the first printout, as I did not produce those. So again, being able to identify these 4 values is important. Sometimes you will only be given the printout and they'll ask you for what does this thing mean? What does it represent? What does it mean in context? You just have to answer the questions. Is there anything I can clarify about the 2 printouts? Right. We can also calculate the equation of the regression line using means and standard deviation of our data set, and also using R. Right, using technology is often the most convenient way to find the equation of a least squares regression line. Yes. It is also possible to calculate the equation of the least squares regression line using only the means and standard deviations of the 2 variables and their correlation. The reality is if you have the list for both variables, right, and you can input the values into 2 lists in your calculator, use your calculator to find the regression line. There's no reason to go through this process unless you're specifically asked to. All right. So we have data on an explanatory variable X and a response variable Y for n individuals. From the data, calculate the means and the standard deviations of the 2 variables and their correlation R. Right, the least squares regression line is the line y hat equals a plus bx with slope b equals r times s sub y, the standard deviation of y, divided by the standard deviation of x. Right, standard deviation of our response variable divided by standard deviation of explanatory variable. It's kind of like a modified rise over run. Remember, rise is y, run is x, finding the slope. And y-intercept, a equals y bar minus b times x bar. Right, so a is equal to the mean of y minus b times the mean of x, which also means you must find the slope before you can find the y-intercept, because we're using b in here. Okay. Anyone need a moment to write anything down from this screen? Please raise your hand. Okay. So now correlation and regression wisdom. All right, here are some things to keep in mind. Correlation and regression are powerful tools for describing the relationship between two variables. When you use these tools, be aware of their limitations. Number one, the distinction between explanatory and response variables is important in regression, meaning making sure that you have the explanatory variable on the x-axis and the response variable on the y-axis makes a big difference. For example, we have our scatter plot with the regression line for the example from yesterday with the Ford F-150 used car, miles driven, and the price. Right. We have our equation, the regression equation, S and R squared. If we switch those and put the price as the X variable and miles driven as Y, so now we're saying price is the explanatory variable and miles driven is the response variable, which doesn't really make sense for context, but if we do it backwards, you see that the equation is entirely different now, our regression line, right? We get a much more steep line showing essentially the same correlation though, right? We'd have the same value of R and R squared between the two, because R and R squared don't care about which one's explanatory and which one's the response, right? The regression equation cares, and it changes the standard deviation of the residuals, all right? And that makes a big difference in like our predictions and things like that, and actually being able to say what this is representing. So we really need to be mindful about setting these up properly. And also keep in mind, if you're using your calculator and you've input everything on lists and you realize that you have list 1 set up as your Y variable and list 2 set up as your X variable and you have them swapped, you don't need to retype them in. Just when you go to do your calculation under stats and everything, just switch the two. Make sure that, because you get to assign which one goes for X and which one goes for Y, just change that instead of retyping your list. All right, once the lists are in, just make sure you're applying them properly. No. So next, correlation and regression lines describe only linear relationships. So here to illustrate this, we have 4 scatter plots. And we can calculate the correlation R and the least squares regression line for any of these, for all of these. We can calculate those because we have 2 quantitative variables. It's possible. All right. So based on that idea, I'm going to ask you guys, which scatter plot of these 4 do you think has the highest correlation? Meaning it has the highest value of R. All right, either really close to +1 or really close to -1. So if you think that graph A or scatter plot A will have the highest value correlation, raise your hand, either virtually or in person. All right. If you think scatter plot B will have the highest correlation, raise your hand. Again, no takers. What about scatter plot C? If you think that will have the highest correlation, please raise your hand. Got a few more takers on this one. All right, and scatter plot D. If you believe scatter plot D will have the highest correlation. A couple takers there. All right, so here's the rub. They're all the same. Each of these scatter plots has the same exact value of R. Okay, meaning that they all have a strong positive association. Right? We're just thinking about what R represents. Now, the other fun thing, all of these have the same exact linear regression line as well. All right. This is to illustrate the fact that even though these have the same R and same linear regression, a linear model is not appropriate for all of these graphs. Just because we can calculate it doesn't mean it's appropriate. Okay? A linear model is not going to properly predict like the next point in graph in scatterplot B. If we follow the pattern, it's going to be somewhere over here. Right? This linear equation here, right, is going to be something like this. However, based on where most of the data is, that's not going to give us a fair prediction of what the next data point should be, based on wherever every other data point is. Right? Correlation and regression lines are only good for linear relationships. Things that we look at and say, a line could do a good job of estimating this. When it's obviously not, like in B, where it's obviously modeled by a curve, we don't want to use these tools. All right, so that's the main point here. Just because we can doesn't mean we should. We need to be kind of critical about when we use this. And also, it's the importance of graphing and plotting the data. If you just looked at all this data and made the calculations and got these results of R and linear regression, you wouldn't know that it's not appropriate unless you made the scatter plot. You might not be able to see it just from the list of data. So graph the data, use your calculator, make a scatter plot. Lastly, correlation and least squares regression lines are not resistant, meaning they're not resistant to outliers. Okay, these values, correlation and least squares, depend on means and standard deviations. Means and standard deviations are not resistant to outliers, which means these things cannot be resistant to outliers because they were calculated with things that aren't resistant to outliers. And to illustrate this, we have this set of data here where most of our data is clustered over around that age, that first word, months, right around 10 to 20. Right, we do have an outlier at child 19 who's a little bit high, right, above the main like cluster, and child 18 that's really far away on the x-axis and in the y direction as well, but not that far from the line. When we remove the outliers one at a time here, we can see how the line changes. If I remove child 19 and keep child 18, the line adjusts closer to child 18. And also R changes. It goes from negative 0.64 to negative 0.76. And obviously the equation changes. If I remove child 18 but keep 19, the line changes again. Right. So because outliers can have such an effect, right, we say these things are not resistant to outliers, which means those extreme points can really throw off those lines as far as predicting future outcomes. All right. Least squares lines make the sum of the squares of the vertical distances to the points as small as possible. Talking about horizontal distance. Right? A point that is extreme in the x direction with no other points near it pulls the line towards itself. We call such points influential. Right? And that's what we have over here with child 18. Right? This child data point is really far away from the main cluster in the X direction. It pulls that line closer to itself. And so it's influential. And again, an outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the Y direction, but not the X direction of a scatter plot, have large residuals. Other outliers may not have large residuals, which just makes sense. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the X direction of a scatter plot are often influential for the least squares regression line. So again, if we look back at this example with the children, whoops, one too many clicks. Right. This data point is influential because when we remove it, we get a large swing in this line. Right. This data point is an outlier, but not necessarily influential because without it, the line doesn't have a huge shift. It still has a shift, but it's not the same as the point that was far away in the X direction. All right, does anyone need a moment to write anything down from this screen? And that brings us to the end of the 3.2 presentation. All right, in this section, we saw how to interpret the slope and y-intercept of a least squares regression line. We can use the least squares regression line to predict y for a given x, calculate and interpret residuals and their standard deviation, mostly using the calculator. Explain the concept of least squares, determine the equation of a least squares regression line using a variety of methods, construct and interpret residual plots to assess whether a linear model is appropriate, assess how well the least squares regression line models the relationship between two variables, describe how the slope, y-intercept, standard deviation of the residuals in R-squared are influenced by outliers, and that's what we were just talking about. And that's it in a nutshell. So now, we're going to look at some examples. That's upside down. That's right side up. There we go. All right, now this may or may not be easier to see on your computer screens than on the projector if you're here live, because my projector kind of is dim. So take that into account. So here we have manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. As soon as the selected customer entered the end of a checkout line, data were collected on the number of customers in line who were in front of the selected customer and the time in seconds until the selected customer was finished with the checkout. The data are shown in the following scatter plot along with the corresponding least squares regression line and computer output. And that's all the stuff right here. All right, so using our output here, our constant, right, that is A. That's the intercept. Customers in line, that represents our variable. That would be B. Let's use a different color. Right. And then down here, S is S. It's the standard deviation of the residuals. And we have our R squared over here. So these are the key values that we want. These are the ones that we're most likely going to need to use. And we have some questions. So, A, identify and interpret in context the estimate of the intercept for the least squares regression line. Right? And you can say the estimate for the intercept is 72.95. Right? And this represents the average time to finish checkout if there's no one in front of you in line. Right? A little over a minute. Right? And so we're just kind of saying what that is in the context. Part B. I'm sorry, I'm not going to write it just in the interest of time. I don't write very fast. If I try to write fast, you won't be able to read it. And that's not useful to anybody. Part B. We're going to identify and interpret in context. Notice how that comes up a lot. Interpret in context. The coefficient of determination, which is the fancy title for R squared. Right. And so again, we have our R squared right here, 73.33%. Right. So that's our value. And this value indicates that 73.33% of the variability in the times it takes customers to finish checkout, including their waiting time when they're not actually being checked out, can be explained by knowing how many customers are in line in front of the selected customer. So knowing how many customers are in front of you, that sounds like a correct sentence, right? You know more about how long it's going to take. 73.3% of the time. This is a good correlation. Okay. And then part C, one of the data points was determined to be an outlier. Circle the point on the scatter plot and explain why the point is considered an outlier. All right. There's only one point that could be an outlier here, and that's this guy right here. Here's our outlier. Okay. This point is considered an outlier because the combination of X and Y values differs from the pattern with the rest of the data. It's far away from a regression line. It's not at all what we would expect based on the other data points. We would not think that if there's 3 people ahead of you in line that it will take about, looks like it's almost the same point as our intercept there, like a little over a minute to get checked out. Doesn't make sense. Doesn't follow the pattern. All right. So the time to finish checkout is just way lower than we would be expected. And so that's why it's an outlier. It doesn't make sense. Right. And that's, for this problem, all that we're being asked to do. And this is actually a problem from the 2018 AP Stats Free Response Questions. Right. Are there any questions about this example? Okay. Now, this is one of the released questions from the first administration of this year's AP exam. In the 2021 Frq question. This one does not start with a scatter plot, but it finishes with them. So we'll look at this question. Attendance at games for a certain baseball team is being investigated by the team owner. The following box plots summarize the attendance measured in as average number of attendees per game for 47 years of the team's existence. The box plot includes the 30 years of games played in the old stadium and the 17 years played in the new stadium. And so here we have our data. Question A asks us to compare the distribution of average attendance between the old and new stadiums. When asked to compare distributions of quantitative data, we need to consider shape, center, and spread. Okay, we've got to think about those things. So as far as shape goes, even though we don't have like a histogram or dot plot to see the actual shape, based on the box plot, we can say that this is most likely going to be symmetric. Right? Our concentration of our data here is in the middle. Or at the very least, it's like it could be like a rectangle of data, right? But it's still rather symmetric. The new stadium data is most likely going to be slightly skewed, right? With the concentration of data. The way that they have this drawn here, it looks like if we were to turn it, it would be to the left. But notice how the numbers are going. This is actually going to be, if we drew it horizontally, we would be skewed to the left with the majority of the data to the right side. So it's kind of plays with the way you see it, but you just kind of have to see where the numbers are going on the scale over here. Right. Lower numbers are at the bottom in this case, which written horizontally, we usually go lower to larger, so it gets a little crazy. But anyway, we have the shape there. So comparatively, the distribution of attendance, of average attendance at the old stadium is basically symmetric or roughly symmetric, as opposed to in the new stadium, where it's probably skewed to the left. So they have a different distribution and a different shape. Right? The center for the old stadium is, basically in the middle, right? It is centered, but the IQR for the old stadium, the middle portion of the data, is slightly smaller and more concentrated than the center for the IQR for the new stadium. It's a little more spread out for the new stadium. Also, the new stadium data is a little more varied, right? It has a larger range compared to the old stadium. And that's it. We've compared shape, center, and spread. We got to do those three things when we're comparing distributions. Right? The other thing to consider, are there outliers? Neither of these has outliers, so that doesn't really come into play, but it's worth mentioning when you write your description. Is there any questions? Anything to clarify about part A here? Following scatter plot shows average attendance versus year. Based on this, it looks like their new stadium opened in 2000. Right? They actually are using different points to represent old stadium and new stadium. Right. And we're being asked, compare the trends in average attendance over time between the old and new stadium. So one way we can do this is to sketch in our best fit line to kind of look at the trend. Right? The old stadium has a slight increase over time. It's not huge, right? But we'll say maybe it's like this. Right? And this is not about having it perfect and accurate. It's just a sketch. We want to see how it compares. Right? And then if we consider the new stadium, right, this is going to be a little bit more steep of an incline. And that's kind of what we need to make our comparison here. Right? Compare the trends in average attendance over time. So both new and old stadium have a positive association between year and average attendance. Right? As the years progress, attendance increase for both. Right? The new stadium seems to have a higher slope, so to say, right? It increases faster over time compared to the old stadium. And that's really about all we can say, because we're not doing any other calculations, right? So yeah, that's how we can make that comparison. The next set of graphs we get for this, 2 more scatter plots. They are both representing the same information, number of games won versus average attendance. Right? The only difference between these two is that graph 2 is showing old stadium versus new stadium data points, and they're kind of mixed in. We do have some new stadium in here with the old stadium stuff. All right. So our first question here. Graph 1 shows the average attendance versus number of games won for each year. Describe the relationship between the variables. All right. Now this is getting into descriptions with our scatter plot, and so we need to talk about the strength of the association, the direction, right? And like kind of the shape. Is it linear? Is it curved? That type of thing. Again, if we were to sketch in a regression line, probably have something like that. Okay, so we can say that there is a strong positive linear association between the number of games won and the average attendance. And we've covered everything right there. One sentence. We've hit all the major things. We have a strong association because the points are clustered closely to our line. It's positive because we're increasing from left to right. It's like a positive slope, right? And it's linear. This can be modeled well with a line. And there we go. Is there anything I can clarify on that? Okay. Graph 2 shows the same information as graph 1, but also indicates the old and new stadiums. Does graph 2 suggest that the rate at which attendance changes as number of games won increases is different in the new stadium compared to the old stadium? Explain. If we look at the data, right, and if we look at the other graph, essentially the answer is no. There isn't really a difference, right? If we drew 2 separate lines, like the increase between games won and average attendance might be slightly different, right? We might have a line here, and then maybe this is actually like a little less steep here. Is there a major difference? Not really. Okay. So basically, no. All right. This does not suggest that the rate at which attendance changes as number of games won increases is different for the 2 stadiums, for the new and the old stadium. That's because they both essentially show a strong positive linear relationship. Right? Essentially the same strength of relationship, right? We can say the slope of that regression line is about the same. Right. Our last question on this one says, consider the 3 variables, number of games won, year, and stadium. Based on the graphs, explain how one of those variables could be a confounding variable in the relationship between average attendance and the other variables. All right. With this, the data and the information we have, the number of games won could be the confounding variable, because it's basically having an effect on the other sets of data, the other relationships. Okay. It's possible that the team winning more games actually caused the attendance to increase, but the games won was associated with stadium. Right? Players maybe performed better because they were in a new stadium. And year, the team developed over time and got better. Right? So using that, having that as a variable could be confounding for us to tell which thing actually has the effect, which one is actually a cause for the increased attendance. Was it the new stadium? Right? Was it development? Was it because we were winning more games? Or is it a combination of these things? We're confounded. Okay. We also know that year and stadium have to be associated, as the new stadium can only be paired with more recent years. We're not going to have any new data for the old stadium. Number of wins may be creating a false perception of an association between stadium or year and attendance. All right. So that's kind of the reasoning. The other thing to consider on questions like this, like making you pick which one's the confounding one, is just have a good argument. Can you back up what you're saying with some of the facts from what you just saw? Right? You might be able to argue that one of the other two variables are the confounding variable. Maybe. Right? There's possibly some wiggle room in that. All right. So those are the examples I wanted to show today because they're specifically dealing with our scatterplots, correlation, all that fun stuff. Doesn't obviously cover everything we saw in chapter 3. It covers a good little chunk. So I'm going to stop sharing my screen. So that being said, next week we will be doing more kind of AP prep stuff, right? So I'll have free response questions from previous year exams that we're going to be looking at, and we're also going to be looking at the grading rubrics that graders use with their reasoning and things that they're looking for, so we can start getting a better idea of how to compose our answers, right? So that's what we'll be spending, essentially we'll be spending time on stuff like that up until we take the exam on the 10th. There will only be a multiple choice assessment for chapter 11 and 3. I'm going to combine it into a single assessment. It's probably going to have 15 questions rather than just 10, but there will not be a free response question for this unit of chapters. Right? I figured trying to get ready for the AP exam will be enough. So I'll try to make that a little easier. Hopefully that assessment will be posted and ready by the end of the week, in which case we'll have a couple of weeks to get it done, because it won't be due until the end of the semester. Well, the 11th, right? Because I need to get your guys, seniors, I need to have your grades ready before the end of the school year, so you can graduate and stuff. So there's that. If there's any questions, comments, concerns, things you need help with, things you want support on, please make sure you're letting me know. I can't help if I don't know. Besides that, I hope you all have a great rest of your day, great rest of your week, an awesome weekend, and I'll see you next week.